Good morning, fourth period. How's it going? Good. It's going good. Good morning. Good morning. All right, so we're starting a new item today, trigonometry. We're going to take Monday, Tuesday, and Wednesday next week to do all the practice examples on how you use it. Today is just introducing it and playing with it a bit more. So I want to take a moment and look at this word trigonometry so you know a little bit more about this word. Trigonometry means triangle measure. And so what it is it's a study of how to measure things using triangles. In this study, we're going to have a new symbol for you. It's like a big capital letter O, but you have to put a belt around it. Now don't pull the belt too tight that your O turns into an 8. It still stays an O. This is a Greek letter, and its name is theta. And it's going to be our go-to angle measure variable. So just like in an equation or in a word problem, when you're asked, hey, give a variable for this, most of you go, oh, x, because that's your big go-to letter for variables. This will be the same thing, but when we're talking about angle measurements, we'll use theta. Theta, yes, and this is what it looks like. Our next new item for today is sine. This is pronounced like the sign on a street, so it's pronounced like that. You'll see it written in word problems this way, which you read as the sine of theta. Okay, we just shortened the word. It's not the sin of theta. The theta isn't a bad boy. No. I'm glad you got that one. Sine. The next one is cosine, and it is pronounced cosine. In a word problem and in equations, it's written this way, cos theta, which is read the cosine of theta. It's not read cos, it's cosine. And the last new one that we have is tangent. Said and pronounced exactly as it seems to read, tangent. And our symbol that we're going to be using in word problems and in algebra equations is tan theta, which I know looks like tan theta, but it's going to be read as tangent of theta. Okay. Take your highlighters if you would, please. This is all the new vocabulary for the moment. And then between each one, give yourself a little divider bar, just so that way there's a little bit more visual separation. Okay. We did some thin ones. Give me a thumbs up when you have this written and down. Thank you. Thank you. Thank you. Let's get 4 more. Thank you. Thank you. 2 more. Thank you. 1 more. Thank you. Okay, I'm going to scoot it up just a little bit. And we're going to look at the first big important bit of information using our new vocabulary words, which are the trigonometric ratios. So in your mind, ratios we've gone over. In your mind, you should go, oh, ratio, that's a fraction. So these are going to be some sort of fraction. Trigonometric ratios are also called trigonometric functions. And the wording for those are kind of interchangeable. We can go back and forth. Okay, I'd like you at this time to please draw a right triangle. Give yourself some space. We're going to do some writing over here. Don't make it too big because we're going to do some writing here on the left. Center it. Have it take up about a third of your note-taking space. Centered. Label the right angle. And then label one of the acute angles as theta. And it doesn't matter which of the acute angles you choose. I'm going to pick this one to be theta. The side across from the right angle is always the hypotenuse. And since we have a right triangle here, I'm going to name that one the hypotenuse. The side directly opposite the angle theta is the opposite side. We're going to call the opposite. We're so creative with these names. The side that's next to the angle theta, but is not the hypotenuse, is called the adjacent, meaning next to. I'm going to zoom in on my note-taking area so that you can see the writing a little more clearly. Bless you. And I'm going to give you the 3 trigonometric ratios. Wait, hang on. I want this in the middle. I want this in the middle. I'm going to do one at a time because I can't think through the... All right, so the first one from above is our sine theta. Our sine theta is given by the ratio of the opposite side divided by the hypotenuse. Here we go. The next ratio is cosine theta, and its ratio is the side adjacent to theta divided by the hypotenuse of your triangle. And then your final trigonometric ratio is tangent, and its ratio is the side opposite divided by the side adjacent to theta. Take your highlighter and give yourself little dividers right here so that each of those looks distinct and different from each other. I'd like to give you what's going to look like the name of a beautiful Native American princess to kind of help you remember the order that these go in. Her name is Side conversations for later, please. Thank you. To-a. So-ka-toa. It basically kind of sounds like the name of a Native American princess. Yeah. And it's just to help you remember how these ratios go together. Okay? That's all it is. A little mind trick for you. Okay. Give me thumbs up when you have all the new vocabulary and new information already situated. Thank you. Thank you. Thank you. Thank you. Thank you. Let me have 3 more. Thank you. There's 1. Thank you. 2. 1 more. Thank you. 3. All right, I'd like to work on some examples. The examples are not going to be using trig yet. I'm saving the trig examples for Monday. Okay? Definitely looking at video 7.4 though. It'll go into more detail and those will have some examples for you. But I'll run our examples on Monday, Tuesday, and Wednesday. So I'd like us to look at an example from our blue books, page 133. And the example I'm about to look at for you is similar to the questions that you see 1 through 6. On 1 through 6, you see some sort of triangle, so please draw a triangle. Don't make it too big today. It's going to mark off a right angle, and it's going to give a variable as one of its sides. Can you please give me a variable? A. Okay? So these sides are A. And I'd like theta. Theta. I'd like, please, now an even number. 8. Okay. The directions for this are going to say, find the value of A. And since you provided the letter and you provided the number, this might not be exactly like one of the questions that are in your book because you created it, but it's going to be similar enough that you can use it to help you. So the first question I have to ask you is, what kind of triangle do you see? A right triangle, which means that we can use which theorem to help us figure out information about their sides? What was the name of this theorem? Yep, we did it yesterday. Yeah, I've heard it from 2 different people. Did you hear them? Did you hear? Yeah, the Pythagorean Theorem. Here you go. But the question I want you guys to ask yourself before you go through the work of the Pythagorean Theorem is, since this is a right triangle, does it look like one of your special right triangles? I'm getting a nod. I'm being told yes, it does. And so the follow-up question that I have is, which one? The middle one. The second one we did, do you remember the name of it?
Nope.
Okay, someone go back to yesterday's notes and help her find out the name of that one. 45, 45, 90. Beautiful. This was definitely a recall moment, yeah? What was our symbol?
Light bulb.
The light bulb? And this was yesterday's stuff? I just put the light bulb and the date. Okay, so in purple, we're going to write down the pattern that you guys had from yesterday for that 45, 45, 90 right triangle that you just told me that this was part of. That pattern had that these side legs were our landmark variable, which they gave us as x because I don't know what's actually there. And the hypotenuse was whatever that landmark happened to be times the square root of 2. Right? You had that from your notes yesterday? Yeah? Okay. Look right here. Those two things need to be the same. There's only one variable in there, yes? Between these two things? So if those two things have to be the same, I can set them equal to each other and use that to help me solve for the variable x, which then will give me this information, which is what I'm really looking for. So how do I get rid of that radical?
What's the difference of a radical and a square root?
Great question, thank you. One thing and one thing only, and that's the number that goes right there on the radical symbol. The square root doesn't have one, so you assume it's a 2. Other radicals are going to have different numbers there. Sometimes at 3, sometimes at 10, sometimes they put a variable in there, which is just plain weird. But that's really the only difference. Other than that, they do the exact same thing. I'm really glad you asked, and you'll play with that a lot next year in Algebra 2. So back to our original question, how do we undo this square root thing? Factor it? Oh, from yesterday, right? I'm so glad that you thought about that. Yesterday, she said to pull those factors up, and it made it kind of go away in some cases. That was for simplifying. In this case, we're trying to solve this equation. We want to get rid of that symbol completely right now because there isn't a way for me to simplify this. 2 isn't a perfect square. Its factors aren't the same. So let's go to this question. Jot it down over here for me if you would please. We're going to talk about inverse operations for just a moment. Yes. You want me to zoom in here on this right side? Sure thing. Let me scoot it over. Thank you, thank you. How's that? Good, okay. So, inverse operations. We have this radical thing, and we want to know what is its versus. Like an epic rap battle. Some of those are really cool. So, its versus, its opposite is the exponent. And that's the little symbol for exponent. So, it's radical versus exponent. So if we're trying to undo the square root, we're going to use the power that goes with the square. So we're going to square everything. All right, so come back over here. We're trying to get rid of this radical. So to get rid of the radical, we're going to square everything. Right? Look what we got here. They'll go more into detail for you next year. So we're just going to do a quick introduction. When you see something that's a bunch of multiplications, I don't have any addition and subtractions in there right now. It's just multiplication. And I'm raising it to some power. I can distribute that power to all of those factors inside. So then this is going to become x squared. And here, they're going to battle it out and disappear. All that's left is that thing inside. And 8 squared is 64. Put a little bar right here so that we can see what's going on. There. Some space. Okay, this looks totally weird, right? It's not how you're used to seeing it. But it's just multiplication in there, isn't it? Which means I can switch the order. There. Whoops. Wait up. Whoops. Had a dyslexic moment. Come back here, number. There we go. Looks better? Okay. You're welcome to do that anytime when you're writing stuff and you see it kind of looking out of order. If you're allowed to switch the order, go for it. All right. I need to solve for x. What do I do? Divide by 2. Why are we dividing by 2? Because what? To get the x by itself. And why did we choose multiplication or division over addition or subtraction? Inverse. Inverse operation, yeah. All right, what's 64 divided by 2? Calculator app, help.
32.
32, thank you. All right, I need to undo the square. How do I undo the square power? The exponent? What's the opposite the inverse? The inverse operation for powers. This is the, exponent or power. They mean the same thing. Sorry. So what's our inverse operation from that exponent power thing? The radical.
Can you give me thing?
Yes, yes. It's the power thing. So if I'm squaring it, then I need to go and take the square root of it. Let's use this pen. Square root square root. We saw this yesterday, right, when we were simplifying the radicals. And we saw it when we were doing distance formula. And now we're going to light bulb moment from yesterday. Light bulb and simplify the radical. Light bulb. All right, so you're looking for factors of 32 where one of them is that perfect square. Give me factors of 32, please. 1 and 32. 16 and 2. Which other ones? 8 and 4. Any others? 3, no. 5, no. 6, no. 4 we have. 7 doesn't work. 9? No. And now we're starting to repeat ourselves, right? Okay. So 8 and 4. Awesome. So which one of these sets has the perfect square in it? The 4? What are the factors of 4? This one will work. This one works. 4 is a perfect square. That'll work. And 16. So now you have two sets with perfect squares. So which one is the best? 16. Why are you saying 16 is the best? Because it sounds legit. Did she just take the words out of your mouth? Yes, you're right. 16 is the best because it's the biggest. So we're going to replace it with that set. It's supposed to be a smiley face. It's all chueco. Do your replacement. I'm going to put the 16 first because the 16 is my perfect square.
Is that radical or not radical?
Where? This?
Yeah.
Radical.
The 16 times 2.
Where?
Is that square root or radical?
The x equals.
This one.
Yeah.
Oh, it's the radical. It's the square root. Yeah. There we go. There we go. Sorry. Remember our special property of radicals from yesterday? Allows us to break the radical into two radicals. There's our special property. Only when it's multiplication, right?
Yes.
Okay. Square root of 16 is?
4.
Thank you.
Yeah.
You knew that. You were testing us, right? There it is.
Listen.
Bless you, bless you, bless you. I gave you like 4 of them already, so I'm banking them for tomorrow. All right. Feels good? We got this? All right. Let's take a moment and scoot over here and do it the Pythagorean Theorem and see what the difference, if any, there is. Okay. So which one of these is the hypotenuse? The 8, because it's across from the right triangle. These have a single variable, so I can totally just use those as the variable for one of my sides, yes? All right, here we go. Going to make my replacements. There's my replacements. I'm going to combine like terms here on the left. But please note that I'm combining them using addition. Yes, sir? Did you see it? Did she answer your question?
Yes.
Okay, thank you very much, ma'am. So I'm going to combine like terms. But please note that I'm combining them with addition. When I combine them with addition, you do not, under any circumstances, when it's addition, change the exponent. When you are combining like terms using addition, do not change the exponent. Next year, you'll be given the rules on how to change the exponents, and I think you were introduced to them a bit last year during Algebra 1. Okay? But as a reminder, when it's addition, don't change that exponent. Okay. Take a look. Look. This line looks an awful lot like that line, doesn't it? So you can see what the answer is going to be already? So the moral of the story, ladies and gentlemen, is that ladies and gents, is that, I'm going to go into my wonderful, horrible accent, is that it doesn't matter which of these two versions you use. If it's a right triangle, the Pythagorean theorem will always work. Thank you. If it's a right triangle, the Pythagorean theorem will always work for you regardless of what kind of triangle you're looking at. If it's a special triangle, you have the option of using the pattern for those special right triangles. Sometimes it makes it easier and you don't have to go through all of this. Okay? The only way for you to know for sure which one will be easiest for you is just to try them both and tell yourself, I liked this one better. And you're probably going to have to do it to a bunch of different problems before you get to the point where you can look at the question and know which pattern is going to be best for you. And it doesn't have to be the same as the person sitting next to you. Okay? All right. I'm going to go ahead and finish this out and then turn off the recording. I'm just going to blast through it since we already know the punchline from the other side. Okay. There it is. And so if I were doing my homework, this is probably all I would write. While you're practicing and you're learning, you'll want to write out all the little steps so you can keep track of it. But once you get comfortable and really practiced, this is just fine.